A piezoelectric sensor is a specific type of sensor that uses a crystalline structure to generate a voltage from a mechanical stress. They are often thin metal sensors that are used in just about every field in many day-to-day products. We can see these sensors in quartz battery watches, electric drum kits, knock sensors for cars, and even medical and aerospace uses. To better understand how they are used, we have to get to know what is the piezoelectric effect, which is the effect that is used in our piezoelectric sensors. The piezoelectric effect comes from a mechanical stress inducing a deformation in these crystal structures. In our sensors, we often see quartz and PTZ ceramic used. These materials have the electrons in the structure displaced to create our electric voltage. The electric dipole density within the material is centered and neutral. The silicon and oxygen in a quartz crystal form a hexagonal shape in this quartz material. The oxygen, being more electronegative, meaning it is more attractive towards electrons, than the silicon, creates these electric dipoles within the material. However, the hexagonal shape offers that centered neutral charge, and as the deformations, our mechanical stress, is created, the hexagon shape flexes. And what was once our centered shape creates a polarization. With the asymmetrical structure for quartz, we can see this polarization, which is an electric field across the whole material, like a large number of voltage sources in series with each other, with each voltage source being that hexagonal shape. We can then measure the electrical field difference across the whole piece of quartz, giving a potential difference, our voltage. Differing materials can offer different voltages and rates. This piezoelectric effect is conversely true. An electric voltage creates deformations in the material. When flipping the direction of the current, we can also see that it will compress when it was once stretching. In electric drums, the drumstick offers the mechanical stress we are looking for to create our voltage. As the stick strikes the pad, the mechanical stress impacts the sensor, which is often made of a brass disc with a ceramic or quartz centerpiece. This deformation of the ceramic material gives that electrical field and voltage, then sending an electrical signal to the circuitry in the drums to give us the drum sound. To see the reversed effect, we look into quartz watches. Within the watch movement, the watch battery provides the voltage to our quartz material. The voltage from the battery deforms the quartz tuning fork, and with its unique asymmetrical structure, like we said before, it oscillates at a constant rate of 32,768 Hz. When these electrical signals are brought to the circuit of the watch, it is able to tick every second with very high accuracy, up to 15 seconds gaining or losing each month. Seeing how a piezoelectric sensor actually reads this voltage is a little different. We know that the piezoelectric effect causes the voltage which gives a current. However, the current from these sensors by themselves is usually very high impedance, which is similar to resistance in where it blocks flow of charges, i.e. current. So we can do a few things to increase the electrical signal from this sensor. First of which, in most applications for these sensors, the actual mechanical stress needs something to travel through to enhance that force for our sensor. Metal plates, foam, rubber are used so that the forces can better travel to our sensor and get a better deformation, thus a better signal. Then from there, the voltage is created through the sensor and it goes through a charge amplifier so we can safely use these voltages and get a better steady current to use. This charge amplifier lets us make the output voltage proportional to the charge from the sensor. Without it, the sensor acts like a high-pass filter in an RC circuit. When viewing these sensors in a completed circuit, we can see a simplified version of these sensors acts like a voltage supply in series with a capacitor. In a traditional piezoelectric sensor, the brass plate and ceramic pad act as the plates for the capacitor. It is best to think of these sensors like a small voltage source in a small capacitor. With these sensors being such high impedance, there's such a small amount of current behind it that even a multimeter would not be able to read it. That is why normally a charge amplifier is needed so that the output voltage from the sensor is usable by making it directly proportional to the charge from the piezoelectric effect. These sensors have important equations you can use to determine the voltage from a piezoelectric effect. The voltage from a piezoelectric effect can be directly calculated if we know the piezoelectric coefficient, force, thickness of material, relative permittivity, vacuum permittivity, and area. If we look further at these equations, we can see that it first starts with the piezoelectric equation and the relationship between polarization and stress within the crystalline structure, where P is equal to polarization, which is equal to the piezoelectric coefficient multiplied by stress. Stress is our force per area unit. Similarly, we can also use the electrostatic equation of a capacitor, where charge is equal to capacitance over voltage. And we can use our polarization. Since polarization is essentially charge per area, we can get polarization is equal to charge over area. Substituting these two equations, we can get that the charge per area is equal to the piezoelectric coefficient multiplied by the force over an area. Now we can finally simplify the equation once again, where we get charge is equal to the piezoelectric coefficient times force. Substituting the equation before, we can set that charge is equal to capacitance times voltage, which is equal to our piezoelectric coefficient multiplied by force. Solving for voltage, we can divide our piezoelectric coefficient multiplied by force divided by our capacitance in order to get our voltage. The capacitance is determined by the permittivity of the material under free stress. So in order to get the capacitance, it is the relative permittivity multiplied by the vacuum permittivity multiplied by area and then divided by thickness of the material. Finally, substituting this equation into our final voltage equation, we get voltage is equal to the piezoelectric coefficient multiplied by force multiplied by thickness divided by the relative in vacuum permittivity and area. Piezoelectric sensors in the piezoelectric effect are one of the most useful sensors we've developed. Used in everyday technology, ranging from phone touch screens to quartz watches, to even medical equipment like digital stethoscopes. There are a lot of benefits to be had from these sensors, and I hope this helped in better understanding this amazing technology and natural effect.